Alright, let's consider polynomial functions. So a polynomial function can be written as f of x is equal to axn plus bxn minus 1 plus cxn minus 2 and so forth to some constant, let's say f. Okay? And basically you can understand that these are basically what we call power functions. And the first term here with the highest power is called the leading term. Now the leading term has the highest power, it's what's called the degree. So the degree is the highest power. And with the degree we can actually we can infer some type of behavior characteristics associated with the polynomial function in question, right? So technically if we had a degree of, let's say, 1, then the behavior of that function is going to look linear. Okay, so a linear equation, right, you would have seen it as y is equal to mx plus b. If there's a degree of 2, it's a quadratic equation, right? So a linear equation would kind of look like this. That's just one example of a linear equation. A quadratic equation is a parabola, right? It can look like this. This is one example of a quadratic equation, right? A degree of 3 is cubic. Excuse me. It's more of like a sigmoid type of function, right? This is a cubic equation, right? So I'm just going to write the common types of each polynomial function. Right, degree of 4 quartic, right, degree of 5 quintic, and it can just keep going on and on. Okay, so the degree is the highest power on a polynomial function. These values, a, b, c, right, for instance, these are what we call coefficients. Now, the value where x is to the power of 0, right, the f value here indicated is a constant. Okay, so the first term with the highest power is called the leading term. Specifically, its coefficient, this a here, this a is called the leading coefficient. Okay, and what makes polynomial functions unique is that these guys actually have constant finite differences. So let's look at this notion of what a finite difference is. Okay, so what is a finite difference? Well, a finite difference in general is basically, I'm going to use FD to represent finite difference. Excuse me. It's the rate of change of y with respect to rate of change of x, right? So it's basically the slope equation, right? And say we had a point of values or a table of values such as this, and let's consider that this is essentially a function. Okay, so I'm just going to plot some values. Okay, and let's say that this is itself a function, and let's figure out the finite differences to show that this is a polynomial function in fact, right? So if we're looking at the finite differences, the first finite differences that I'm going to be looking at are called the first differences. Okay, so I'm going to call these the first differences. Okay, let's use lowercase fd for that. Excuse me. So the first finite differences are called the first differences, and you can notice here that the change in the x value is constant here. So we actually don't need to calculate it because we actually created a constant x value just for simplicity's sake. Okay, the difference here is -1 minus -8, which is 7, 0 minus -1, which is 1, 1 minus 0, which is 1, and 8 minus 1, which is 7. Okay, so these are our first differences. Okay, and you basically would divide it over 1, but it's going to give you the same number. Okay, now we stated that all polynomial functions have a constant set of finite differences, right? So all polynomial functions have a constant set of finite differences. So at one point, the finite differences will all be constant. Okay, And whatever finite differences are constant will also reflect the degree of the function. So we'll actually take a look at that through example. Like if the second finite differences are constant, it's a second degree function. If the third finite differences are constant, it's a third degree function. Now you can imagine here that the first finite differences are not constant. So what we do is we look at the next finite differences. So the second finite differences are called the second differences. Okay, so look at the second differences. You do 1 subtracted by 7, which is negative 6, 1 subtracted by 1, which is 0, and 7 subtracted by 1, which is 6. Okay, and then you can see that this is still not constant, so we look at our next set of finite differences, the third finite differences, and you can see 0 minus negative 6 is 6, and 6 minus 0 is 6. Okay, you can actually see that the third finite differences are constant. Right, so because we have a set of finite differences that are constant, excuse me. So because we have a set of finite differences that are constant, then this implies that we do have a polynomial function. So this actually verifies that we have a polynomial function, right? So this indicates that we have a polynomial function. Well, this also tells us that because the third finite differences are constant, this is a function with a degree of 3. So as a result, it should have a cubic sort of behavior, right? So it should kind of resemble this S-shaped or sigmoidal curve, right? So this is a cubic function, it's a degree of 3, right? Well, actually knowing the finite differences and the degree of the function, we can actually determine the leading coefficient, right? So I'm going to show you guys how to find the leading coefficient. So the value of the finite differences here are 6, right? The value of our degree here is 3. As a result, we can understand that our cubic function f of x should be in the form of ax cubed plus bx squared plus cx to power 1 plus d, right? Because we're using this general template that I outlined out here. F of x is equal to axn plus bxn minus 1 plus cxn minus 2 and so forth, right? So we're using that template to kind of demonstrate that. So that's why I got this. And we know that this is a cubic function. We want to figure out, let's figure out the leading coefficient. How do I figure out this a value? Okay, I'm going to explain why this is really useful later on, but right now, how do we determine the a value? Well, in this case, there is an equation, right? The leading coefficient times the degree factorial is equal to the finite difference. Okay, so this is an equation that you might want to remember. It's really useful in terms of finding your leading coefficient. So this is the equation. So once again, the a here represents your leading coefficient. Excuse me. The n represents the degree, and the fd represents the finite differences. Okay, so if you wanted to solve for a is equal to the finite differences over the n factorial, right? So let's solve for a here, right? Now what does this factorial mean? Well, a factorial, it's usually used in counting principle, especially when we're looking at arranging a certain number of elements a certain number of ways, right? So it's a study called permutations. For simplicity's sake, we just need to memorize what it means. So for instance, if I have 5 factorial, this is like 5 times 3 times 2, 5 times 4 times 3 times 2 times 1. If I had 9 factorial, this is like 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. If I had 4 factorial, this is like 4 times 3 times 2 times 1. So you get the picture behind this, right? So our leading coefficient here, the finite difference value that was constant is 6, right? You want to make sure that it's the finite differences that are constant. Okay, specifically it's the value of the finite difference that are constant, right? A here is the finite difference, 6 over n factorial, which is 3 factorial, and 3 factorial is 3 times 2 times 1, which is 6 over 6, and a is equal to 1. So this tells us that our leading coefficient is no other than 1. So our function here, just from knowing that, our leading term here is x cubed. Okay, and to find the rest of your coefficients like b and c and your constant d, you need to actually plug in points to do that. Okay, But beyond that, we just figured out a way to figure out the leading coefficient. So once again, polynomial functions have constant finite differences. Whichever finite differences are constant will reflect the degree of the function. By knowing the degree of the function, we can figure out a general aspect of its shape. Okay, so now we'll consider some other properties of polynomial functions, specifically their behavior and their end behaviors.